Let's take some time to discuss the rates of which different carboxylic acid derivatives react. We've talked about the general trend from, if we move up from amide to ester to carboxylic acid itself, which isn't drawn here, to anhydride to acid chloride, that the derivatives are more reactive and they're reactive, and therefore will react faster. And let's take a few minutes to talk about why. And there are really two ways we could think about this. One would be considering the quality of the leaving group. And if we think about each of these leaving groups after it's left, and we think about the relative stabilities of those leaving groups, we'd have consider chloride, acetate, an alkoxide, and an amide. As we move down the table, these are less stable, right? So if we think about the oxygen with resonance, the oxygen anion without resonance, or making a resonance comparison, if we think about an oxygen versus a nitrogen, we're making an electronegativity comparison. And we think about how chloride fits into the scheme of things, we're thinking about its conjugate acid being a strong acid or a mineral acid. And so it's going to be a much stronger acid, therefore it's a much weaker base than any of these organic bases. So it's a good chance to revisit acid-base chemistry. Another way to think about it, now, by the way, one of the drawbacks, of course, is that if we're doing acid catalyzed hydrolysis, these really aren't the leaving groups, because we wouldn't be making O minuses or N minuses in acid, but the general trend still holds. Another way to think about it would be to think about the size of the partial positive charge on the carbonyl carbon. When we have a halogen, which are more electronegative than oxygens, which are more electronegative in turn than nitrogens. So the partial plus here would be relatively small. The partial plus here is bigger. The partial plus here with another oxygen inductively adding to the electron withdrawing effect of the first oxygen is going to be larger still. And perhaps we didn't draw this one big enough. This would be the biggest partial plus of all. So let's look at some examples. And one thing that we might just simply be asked to do is to compare the relative reactivity of a series or one or more carboxylic acid derivatives. So if we're asked to compare or explain which one of these is more reactive, with, let's say, hydroxide, which would be basic hydrolysis, which would it be? We would choose the anhydride because you are thinking about quality of the leaving group or partial positive charge on the carbonyl carbon, either which is going to be bigger partial charge here because oxygen is more electronegative than nitrogen, but also think of this being a better leaving group than the nitrogen. Let's consider an example where we have two of the same functional groups so that we can apply some of the same ideas and extend them into, or extend our thinking into other things that we've known or studied over the years. Let's imagine that we have these two anhydrides, same functional group, so potentially the same leaving group. What's the difference? The difference is in the size or steric hindrance involved in the groups nearby the carbonyls. On one anhydride, we have relatively small ethyl groups. In the second anhydride, we have relatively bulky tert-butyl groups. So we might think about one of the rate limiters being the approach of the nucleophile to the carbonyl carbon, which would be relatively uninhibited in the case of the less bulky anhydride, but would be more difficult and therefore happen more slowly with a larger tert-butyl group. So we would expect a faster acyl substitution reaction to be the less hindered compound. What about a pair of esters where the only difference is the alcohol functional group on one has fluorines, where the other one has hydrogens? If we think about the effect of the fluorines, two ways to look at it, right? One would be the stability of the leaving group after it's left. The other would be the effect of the fluorines on the carbonyl oxygen's partial positive charge to begin with. Now we know that fluorines are extremely electronegative or electron withdrawing, so they're pulling electrons away from the elements they're attached to. That would stabilize the trifluoromethoxide relative to plain old methoxide, making a better leaving group that could potentially accelerate the reaction. The other thing we could think about is the size of the partial positive charge on the carbonyl oxygen. If we put a bunch of fluorines here, we're pulling even more electrons away from the carbonyl carbon. It's an inductive or an indirect effect, but it's still worth noting. So we'll just make that a smaller, more modest partial positive. And either of those factors would favor the trifluoromethylbenzoate reacting faster.